Well, hi, welcome again to Math 315. This is the third recording in Chapter 2, and we've been looking at sequences and convergence of sequences using the epsilon m definition. Now, we finished off last time by just commenting that we would like to be able to simply apply the basic heuristic tools that we've been using before in order to work out sequences or work out limits of sequences without having necessarily to go through all the epsilon m definition. And the following theorem basically tells us that doing what we've been doing before, that is using our intuition, in fact actually is mathematically correct. It's sometimes referred to as the algebra of limits. So when asked to calculate a limit, if you are expected to do it by epsilon m, then I'll explicitly say so. Otherwise, we will simply use our basic knowledge, our basic common sense to work out these limits of sequences. So here is our theorem, the so-called algebra of limits. So that a and b are sequences which converge respectively to some numbers a and b. So an goes to a, bn goes to b. Then the first result says the limit of an plus bn, as you might expect, is just the sum of the limits. That is, if I add the sequences and then take a limit, then I just get the sum of the limits of the two sequences. This is what we normally do if we've got various terms. We'll look at each term separately and then just take limits and add them all up. The second one says we can multiply the terms of the two sequences together and then take a limit, and the limit of that is just the product of the limits. And the third one says that if we take a quotient of limits, then the limit of the quotient is just the quotient of the limits, provided we're not dividing by 0 at any stage. Otherwise, crazy things can happen. So the bn's can't be 0 for any n, and the final limit can't be 0. Now, I'm going to go through the proofs of this again. I don't expect you to be able to reproduce all of these proofs. The first one is not too hard, actually, and it's similar to what we've been doing. And there is a tutorial problem where you'll be looking at what happens if you take a sequence and multiply it by lambda. So you'll get a little bit more practice at this, but the second part of the proof, the one for this bit, is complicated. So I'm only going to do 1 and 3, and if you can follow 1 carefully, that's good. If you can manage to follow what I'm doing in 2, that's even better. Now we go back, of course, we've got to go back to the definitions. So when we say that an goes to a and bn goes to b, then that means that if I take any epsilon bigger than 0, then there's an m1 such that an minus a is less than epsilon on 2, provided I go far enough. I take n bigger than m1, and there exists an m2 such that bn minus b is less than epsilon on 2, again provided I go far enough, that is if n is bigger than m2. Now note again that I've chosen epsilon over 2 here rather than epsilon, simply to give an elegant last line. It really makes no difference. If this is less than epsilon, then I just push a bit further on until it's less than epsilon on 2. So what I'm going to do is I'm then going to take the bigger of these two numbers so that everything works. So I'm going to take n bigger than the maximum of these two, and that means I get both of these results hold true. And I'm trying to look now at the sum. So I'm looking at an plus bn, and I claim that the limit of this is a plus b. So I subtract this sequence minus what I claim to be the limit. And I'm going to re-bracket these. I'm going to write this here as, I'll just pop this in here, this is an minus a, bracket those together, plus bn minus b, bracket those together. And now I can use the triangle inequality on that one and say that this is less than absolute value of this one plus absolute value of that one. And now we saw that provided I go far enough, which I have, then this is less than epsilon on 2 by what we did above here. That's what we had up here. And the second term is also less than epsilon on 2 by what we had here. And if you add those, you get epsilon. So that means the first result is true. Now that proof is not that difficult to do. That proof is not that hard. The second one is a lot more tricky. I basically sort of worked backwards from what I wanted and then made it be, chose the various terms to make everything come out slickly at the end. So for the second one, I'm looking now at the product an and bn. So once again, if an goes to a, then given epsilon bigger than naught, I can find an m, I can go far enough. Provided I go far enough, then I can make an minus a less than, I'm going to, instead of just epsilon, I'm going to put epsilon on 2L. Now what is L? Well, I needed to come back here that by the lemma, this Bn, this sequence is bounded, and so by the lemma, it's bounded by something, so I'm going to say it's bounded by L. So, and that's where the L's coming in here. Okay, so if Bn is bounded, then its absolute value is less than L. There is an L that bounds this thing. Now, again, if epsilon's bigger than naught, if I go far enough along the first sequence, the ANs, then I can make that difference, the sequence minus its limit, I can make as small as I like, so I make it less than epsilon on 2L. And the Bn's go to B, so again, if I go far enough, if I take n bigger than some number m2, then the difference between Bn and B in absolute value is less than epsilon. This time I choose epsilon on twice the absolute value of A. That's the limit of the first sequence. I choose these simply because, you'll see why I do that in a minute, I simply choose these rather than just epsilons. I choose these to make it all come out slickly at the end. As I said, this is a more difficult proof. Now, hence, I'm going to go make sure I go far enough, so I'll go beyond the maximum of m1 and m2 so that all of these inequalities hold. And then what am I doing? I'm looking at the product of a and bn minus the product of the limits. And I want to squeeze this less than epsilon. So what I do here is I'm going to add and subtract something, or subtract and add the same term. So I'm going to subtract a times bn, and I'm going to add a times bn. So it doesn't change anything, I'm just subtracting and adding the same thing. And then I can factor a bn out of these two terms, which is what I do here. And here I can factor an a out of these two terms, which is what I get here. And now I can apply the triangle inequality. So that's less or equal to the absolute value of this, which is the absolute value of an minus b, times the absolute value of b sub n, plus the absolute value of that, which is absolute value of a, absolute value bn minus b. And now you see why I chose these various things, because the an minus a up here was less than epsilon on 2L, so I popped that in there. The bn's were bounded, and we said that so the absolute value of bn was less than L. The absolute value of a I just copy down, and the absolute value of bn minus b, well, we saw up here, we chose it so that that was less than epsilon on 2a. And the point is, when you simplify this expression here, the L's cancel, I just get epsilon over 2 again. And the A's cancel, so again I get epsilon over 2. And that, of course, is just epsilon. So that's a harder proof. I don't expect you to be able to reproduce that. If you can follow the logic of it, then that's great. You should be able to follow the proof of the first one. That wasn't quite so difficult. Now, what's the point? What does this allow me to do then? Well, now it allows me to use my common sense. So if I'm working out this limit here, then what we do is we do what we normally do, that is we ask where's the money. Well, there's an n squared on the top, that's the dominant term. We get 2n squared on the bottom, that's the dominant term. And we then divide by the highest power of n in the denominator, which is n squared. And so this is the limit of 1 plus 6 on n squared, limit 2 plus 1 on n squared. And now, normally we would just go straight to the answer here, but just to demonstrate what that theorem is about in this context, what we're doing now is we've got a limit of the quotient is the quotient of the limits. So I can split this into the limit of the top divided by limit of the bottom. And then I can split this limit into each of these two terms on the top. So that's the limit of 1 plus 6 on n squared is the limit of 1 plus 6 times the limit of 1 over n all squared. I'm there using the fact that we can split up the sum and we can take the 6 out, and I can write 1 on n squared as the limit of 1 on n all squared. So I'm using that previous theorem, and when you do that, of course, you just get 1. And you do the same thing in the denominator. You get the limit of 2 plus the limit of 1 on n all squared, and that gives you, the denominator gives you 2. Finally, you put it all together and you get a half. Now, in practice, you're not going to put all those steps in. In practice, you're going to just do this, as we've been doing before. You divide by the highest power of n in the denominator, and then you're just going to go straight to the answer. And so I've done one more example of this. If it says use the algebra of limits to find this limit, well, this is all we have to do. We just do what we've been doing up till now. So here we're working 2n squared plus 4n minus 1 over 4n squared minus 2n plus 3. So again, you say, where's the money? Well, there's a 2n squared on the top. There's a 4n squared on the bottom. So the highest power of n in the denominator is n squared. I'm going to divide everything in sight by n squared, as we've been doing. We get that expression. I'll leave you to check that. We divide the bottom by n squared. We get that. And now we're just going to say, look, that goes to naught, that goes to naught, that goes to naught, that goes to naught. So all that survives is 2 on 4, which is a half. So all we're doing at this point is showing that, very formally using our epsilon m definition, that the sort of things we've been doing up till now, heuristically, by a little bit of hand waving, actually works. And that's what we'll be using from now on. Now, I just state without proof a couple of little basic facts here, and the first one says that, well, it says if A and B are both convergent sequences, then if an is less than bn, in other words, these terms are always less than these terms if you draw a picture of them. So you've got an an, if I draw a little picture here for the first one, so if you've got some ans here, and you've got some bn's here, and if this one goes towards some number b and this goes to some number a, so these are the ans, these are the bn's, then all it says is that when you take the limit, this a, the limit of the ans, is going to be less or equal to the limit of the bn's. In other words, taking limits preserves inequalities. It doesn't upset the inequalities. More useful, indeed, is the second one that says if you've got a sequence C that's somehow trapped between the an and the bn, then using this idea here, the limit of the an is less than cn is less than bn. That means the limit of this one is squeezed between these two limits. So it's a little bit like our pinching theorem that we saw before for limits of functions. So if I've got two sequences, an and bn, and there's a cn here, then this limit is trapped between these two. In particular, if the limit of this one, the an's, equals the limit of the bn's, then this one will exist and will equal this limit here. So I might just mention that here. It's very useful if the limits of ANs and BNs are equal. So I might just write that here. So if the limit as n goes to infinity of AN equals the limit as n goes to infinity of BN, then the limit as n goes to infinity of Cn exists and equals these ones. I'll call that L and equals L. And that's a version now of the pinching theorem. And I will do an example of that. We'll see some more examples of that one in the tutorial problems. So we're going to find the limit 1 over n sine of n. Now again, heuristically, just by common sense, you might say, well, look, the sine n's are bounded. They can't be very big. They wobble all over the place, but they're bounded. And the 1 over n is going to 0, so we'd expect this limit to be 0. But if we're proving this formally using the pinching theorem, we would do something like this. We would say, here's our limit, and what I want to do is I want to take this here and pinch it. So I'm going to say, well, sine n can't be any bigger than 1, so this is less than 1 over n sine n. And on the other hand, it's bigger or equal to minus 1, so this bigger than minus 1 on n. And we know that each of these goes to 0. And so one way of writing this that I often will use is this. I'll simply put an arrow down here indicating that this sequence goes to 0 and this sequence goes to 0. So that means the limit as n goes to infinity 1 on n sine n exists, and it equals 0 by the pinching theorem. Equals 0 by the pinching theorem. Now I have mentioned before, and I wanted to spend just a little bit of time on this. I'm going to use some integration. I haven't done integration in this yet, and we won't be, but I'm going to use some basic calculus here in this next problem. I mentioned this rather intriguing limit. This limit as n goes to infinity of 1 plus 1 on n to the n. The limit as n goes to infinity 1 plus 1 on n to the n. And I mentioned before that you can get the wrong answer here by trying to use your intuition and say, well, if n becomes very big, then 1 over n goes to 0, and then you've got 1 to anything is 1. So you might guess the answer to this limit's 1, but in fact it's not. As we'll see, this limit is not 1. And I wanted to just say a little bit more about this limit because this is a very fascinating limit. So before I come to the analysis of it, I thought I might just mention a little bit of the background to this particular limit. This limit was of interest to the medieval bankers during medieval times. Why on earth would they be interested in this limit? Well, they wouldn't have thought about it the way we are going to think about it, but they asked the following question. If I invest $1 at the outrageous interest rate of 100% per annum, so I take $1 and I find some fool that will give me 100% per annum. And I ask myself, well, okay, at the end of the year, how much will I have? So after 1 year, we have, well, I have the dollar I started with, plus I get 100% of it, so I will have $2 at the end of the year. Okay, fair enough. So I've doubled my money. On the other hand, if we paid half the interest after 6 months, pay half the interest after 6 months, then what would I get? Well, I would only get 50%, so I'd get $1.50. And now I pay 100%, sorry, I pay 50% of this in the next 6 months. So, and after a further 6 months, we get Well, I'm going to get 50% of that, which is 75 cents. And so that gives me a total now of, adding these together, I get $2.25. Aha! If I just paid the interest after 1 year, I only get $2. If I pay the interest after 6 months and then add it in, if I now add it in, so I take 50% added in, I get $1.50. And now I take 50% of that, which is 0.75, and add it in, I get a total of $2.25. Look, I've made more money. Well, the medieval bankers thought this was a lovely idea. It's called compound interest. And now you ask the question, well, what if I paid the interest after 1 month? So I take 1/12 of this and work it out and add it in, and I keep doing this every month. At the end of 12 months, I would make more money. I didn't calculate what it is, but you make more money if you compound it every month. Well, they were quite greedy, the medieval bankers, and they said, well, what happens if I do it not every month, but every week? I make more money. What about if I make it every day? More money. Every hour, every minute, every second. Can I make an arbitrarily large amount of money? Can I make more and more money? And the answer is no. The most you can make is about $2.71, as we'll see. That's the maximum. You can't make infinitely much money. So we're going to recall our compound interest formula, which I'm sure you did back at school. So the compound interest formula is P into 1 plus R on 100 all to the n. That's the amount that you make. P is the amount you invested. So I invested $1, so that's just $1. R is the interest rate. Now remember, that's the interest rate per annum. So I'm going to divide it into n equal periods of time. So here I did it in 2 equal periods of time every 6 months, or I might do it every month, and it'd be 12 equal periods of time, and so on. And that means the R in this case would be equal to, I take 100%, but I've got to divide that by n. And when I plug this into here, so P is 1 and R is 100 over n, then I get, aha, here is our expression, 1 plus 1 on n to the n. So the medieval bankers said, how big can this be? The bigger I take n. So I pay the interest after n equal periods of time, and I make it bigger and bigger and bigger. Can I make, how much money can I make on this? And it turns out you can make about $2.71. That's what we're about to show. That's just a little bit of background to this rather fascinating limit. So there's the limit, and we're going to use the pinching theorem, in fact, plus some calculus to actually find the correct value of this limit. And this is actually one of my favourite results in mathematics, because it's so simple. It's remarkably beautiful and remarkably simple. I hope you agree. Once you get started, once I tell you how to begin. So I'm going to take the function 1 over x, and I'm going to look at the area under the curve between the integers n and n plus 1. That's all I'm going to do. And I'm going to look at some rectangles. So the area under the curve, that's given by the integral of 1 over x from n up to n plus 1. So that's giving me this area in here, the area under the curve between these two. So I'm going to draw a little rectangle here, where it cuts the curve here, and the y value is going to be 1 over n plus 1, because the function's 1 over x. So a lower value of the area, a lower bound on the area, is going to be the area of this rectangle. So the true area is bigger than this little rectangle in here, whose width is 1, there's a gap of 1 here, and whose height is 1 on n plus 1. On the other hand, I can over-approximate the area by building a big rectangle here using this endpoint, and that's got width 1 and the height of this one is 1 over n. So this gives me a little bound on how big the area. So this area has got to be bigger than that but less than that. Now I'm going to integrate this, and if I integrate 1 over x, I get log x. Put in the endpoints and subtract, I get log of n plus 1 minus log of n. And then I'm going to multiply everything through by n. So I get n on n plus 1 is less than n times this difference is less than 1. I've multiplied by n. Now I'm going to use the log laws next. I'm tempted to use the log laws here, so I'm going to pull this underneath. This will be the log of n plus 1 divided by n using the log laws, and then I can pull this n right up to the top, and that's what I'm going to do. I'm sorry, it's on the next page. So all I've done there is I've written this as this was the log of n plus 1 over n, and there was an n out the front here, so I've used the log laws to pull it underneath, and I can then pull the n up to the top. That goes up here, and I just divide. N into n goes 1 plus 1 on n, and there tantalizingly is that expression that we started with, and it's still bounded between n and n plus 1 and 1. Now I use the pinching theorem. I'm going to take a limit as n becomes very big. And we can see by inspection that this is going to 1, and this is 1. So by the pinching theorem, this limit exists, and in fact it goes to 1 as n goes to infinity. If I now raise both sides to the power of e, then e to the log, they cancel out, and I just get 1 plus 1 of n to the n, and I get e to the 1, which is e. So in fact, this limit turns out to be our old friend e, which is 2.718282 approximately, and as I mentioned, that means the medieval bankers could only make about 2, so this is approximately 2.71, and that means the medieval bankers could only make at most $2.71 from their dollar using that 100% interest rate and compounding over in smaller and smaller periods of time. So that is a nice example, and I hope perhaps you may have seen this limit before. If not, it's one that you should be familiar with. Okay, that will do for this one, and we'll finish off in the next lecture. We're going to have a look at recursively defined functions and the monotone convergence theorem.